This term on algebraic surfaces. And the ultimate aim, although we won't necessarily get that far, is some cases in which you can describe all surfaces with given invariance. So, e.g. Godot surfaces, which means PG equals 0, k squared equals 1. So I've worked on this particular single case almost all of my life, so almost all of my career. So it's a very big case. Anyway, we won't really get very far. So this problem is about existence, whether these surfaces exist, and also about their construction and their moduli and other matters. And we can describe, this is usually related to graded ring constructions. So, this is a big subject, and it doesn't apply just to surfaces. If you want to study three-folds or four-folds or other algebraic varieties, sooner or later you're going to be involved in complicated constructions involving commutative algebra, involving rings, graded rings, and possibly modules over rings. Okay, so that's just the aim. As I said, we won't necessarily get that far during the whole term. So let me start with much simpler matters. So last term, and I'm sure everybody here has heard Riemann-Roch on curves. So I've got a curve C, genus G. Curve means here for the moment non-singular projective curve. And then we can talk about the question about maps from C to projective space. Let me just write maps to P some A. Right? Or we can talk about space of functions. So this Riemann-Roch space L of D. So this is a finite dimensional vector space of rational functions. Or we can talk about linear systems. D. And so D, this is, what this really is P1 plus P2 plus PD. And these are, so we want to think of this as, so here's my curve maybe, and here are my points. And these points, this is a kind of group of points, and they're sort of racing up and down the curve. They're moving up and down the curve. So these three things on the face of it look quite different. It's not very difficult to relate them, and I'm sure that you've all seen this in the course of studying Riemann-Roch. If I want to go from here to here, then I choose a basis of the space, and these are rational maps, so they define a rational map from C to projective space. Okay, so the linear system is the zeros of the functions after you've cleared common denominators, after you've arranged this to be a morphism. Okay, so this is basically simple framework in which you can do lots of different work for algebraic curves. So if I want to take the same idea applied to surfaces, then immediately it's more complicated, because so what I want to think, I can say I'm going to have an S, a non-singular surface, non-singular projective. But then when I start talking about maps to projective space, it will actually happen definitely, that the map is not a morphism, that I have to do blow-ups. So the map may not be a morphism. And if I take a linear system, D, then this is maybe some curve C1 plus C. I don't know. It won't be. It's not the same number D, but let's just think of it like this. So here's my surface, and here are some curves. And the curves, I want to think of the curves as sort of racing around here, but lots of different things will happen. So the curves themselves have internal geometry. The way the different curves intersect also has some geometric properties. Whether this possibility that the map is not defined everywhere corresponds to points of the variety where all of the curves pass. So all of the curves, all of these functions, even after I've removed denominators, still have poles, still have a lot of common, a point at which all of the functions have a common zero. So this map is not well defined. And so the first thing we need is intersection number of curves, intersection numbers of curves on S. Right, and of course we're going to need a whole lot more apparatus before we can really get anywhere. So most of today's talk I'm going to be talking about this problem, introducing intersection numbers on curves. Intersection number of, so this means D1 times D2, some number. I want to discuss this. So there's sort of little technicalities here. I'm not going to do it formally or completely. So I hope everybody is aware of this book. We will make copies of this available to anybody who needs it. So these are lectures I gave in 1990s, actually starting at University of Utah when Professor Youngnan was still a graduate student. But I gave these in Park City and wrote a first volume of lecture notes, and I hope the lectures I'm giving now will be a second volume of lecture notes. So I don't want to repeat everything that I said there. In particular, intersection number on surfaces. There's this book has a funny property that the chapters are called Chapter 1, Chapter 2, and then Chapter A, Chapter B. So the organisation is not very standard, but anyway, Chapter A of Park City so Park City means these lectures called chapters on algebraic surfaces. This is intersection numbers. And I'm going to make some commentary on intersection numbers. I'm not going to give a correct or a complete treatment of them, but I'm going to go in one or two directions that we really need immediately. So the immediate aim, I want to talk about how to map a surface to projective space using the canonical system or multiples of the canonical system. So I'm going to explain some of these things in more detail, or at least talk about them. So I want to give one or two examples. So these are very simple examples. So, when you give an example, there are different reasons for doing it. These examples, I'm trying to say one or two of the things that we're aiming to do without any technicalities at all. So there's practically no technicalities involved here. So first of all, let me give, this is example 1. And this is something which I hope everybody has thought about in connection with Riemann-Roch on curves. So see a curve of genus 3. And we're going to look at the canonical class and the map phi kc from C to P2, which it defines. Okay, so as I said, I hope everybody remembers Riemann-Roch on a curve. In particular, Riemann-Roch on a curve says that there exists this magic device of the canonical class, and it has the property that L of Kc is three-dimensional. So this is a three-dimensional vector space. This is the genus. And the degree of Kc is 4. So if I want to think of it like this, it's 4 points racing around a curve. Okay, so three-dimensional means if I choose a basis, so I choose a basis, call it F0, F1, F2, then I use the map, I use the ratio F0, F1 to F2 as a way of mapping C into P2. So so these guys, F0, F1, F2, they're rational functions, and they have poles at most some given canonical divisor C. So I can take an effective divisor here, then 4 points, right? Then you can show that L of Kc, this is a very trivial corollary of the Riemann-Roch theorem. So this is not equal for all P. And so this means that, that this map here, phi kc, is a morphism. It's not a matter of we have to extend a map to as a morphism. It's a morphism as given. So to P2 is a morphism with the property that if I take the pullback of O P1, P2 of 1, so if I take the linear system of planes in P2, the linear system of lines in P2, and pull them back, then I get these 4 points. This is H0 of, this is L of Kc. Right? And so the picture I have in mind is, here's my P2, here's my abstract curve, and here's the map into P2. It's going in like this, and when I take the pullback of the family of lines in P2, I'm getting this family of points running around the divisor. Right? And so because this is 4, it means if I take the inverse image of a line in P2, I get 4 points.
Okay, your picture is in not hyperelliptic case.
I'm sorry?
Your picture is given in the not hyperelliptic case.
You're trying to steal my joke.
Sorry, no, because you made the picture. No, I didn't want to steal your joke.
So as Francesco was slightly anticipatedly. So if I take a line in P2 and take the pullback of the line, so this means I intersect here and then I take all the inverse images of all these points, then this is a divisor in KC. So this is 4 points. And so it follows, therefore the degree of phi times the degree of the image is 4, and there are only two cases. This is 4 and 1, or 2 and 2. So I mean, this is I hope everybody has seen this in the first exercise you do after you establish Riemann-Roch. So there are two cases. Phi kc takes C and embeds it as C4 in P2. Right. So then we say that kc is very ample. Right, and this happens if and only if L of Kc minus P minus Q contained in L of Kc has codimension 2 for all P, Q. Right, so this guy is three-dimensional. It means if and only if. For every pair of points P and Q, they impose linearly independent conditions on sections of Kc. Right? So, or C is 2 to 1 to a quadric curve, a conic curve in P2. So this is a non-singular conic. Right? In this case, as we know, I think from my first lecture last term, the conic is isomorphic to P1. Right, so this is a map C, 2 to 1 to P1, and then the P1 is embedded. This is this second Veronese embedding of P1 into P2. Right, and in this case, it happens that in this case there are 8 branch points. Right. So to summarize, in this case, this is the hyperelliptic case, and this is the non-hyperelliptic case. So this is Europeans are brought up on Christian mythology. In Christian mythology, after God created the world, there was the Garden of Eden where Adam and Eve lived happily. So everything was very happy and very wonderful. So this is a kind of Garden of Eden. This is the absolutely perfect case where everything in algebraic geometry is understood, where you take the simplest idea and it just works straight away. And so the real world is not like that. Quite soon, they get thrown out into the real world. When we're going to be working with algebraic surfaces, and then everything is going to get much, much harder. But this sort of shows you the thing that we'd really like to happen in the perfect case. Okay, so I've been talking here geometrically in terms of the geometry of the map, or in terms of the cohomology, the base points and so on of linear systems. And so on. But there's another way of thinking about this, which is that I make this ring Kc. So this is the direct sum H0 of n Kc. So here I'm taking the vector spaces L of Kc, and L of n kc for all n, and I'm building them up all together into one ring. So this is the graded ring corresponding to C. So it's also called the canonical ring. Right, so canonical ring because this is the canonical class. So in this case it's K of x1, x2, x3 divided by F4. Right, so this x1, x2, x3, it's the same as F0, F1, F2. Right, so in this case I ask, if I ask, for example, who are the sections of H0 of 2K, and, well, this x1 is a section of K, and so this includes x1 squared and x1, x2, and so on. Altogether 6 elements. And this guy is 6-dimensional, and these guys are 6 elements in it, and they're linearly independent, so they're a basis. And then the same thing happens in 3 dimensions, in degree 3. In degree 4, the space H0 of 4K is 14-dimensional, as you can check by Riemann-Roch, whereas there are 15 monomials here, so there must be a relation. Right? So in this case, the ring of Kc is just a little bit more complicated. It is K of x1, x2, x3, and then there's going to be a quadratic relation between them. So there's a quadratic relation, the equation of this Q. So in this case, I take the same 6 generators here, the same 6 monomials in the basis of Kc. I get 6 elements in 2K. It's 6 elements in a 6-dimensional vector space, and for better or for worse, unluckily or by design, they're linearly dependent. So there's a guy Q here. If they're linearly dependent, I must have a new element y here. So this y has degree 2. Right? and then there's going to be another equation in degree 4. And this equation in degree 4 is really saying that y squared equals, I don't know, g4 of x1, x2, x3. Right? And this g4 intersect q is the 8 points, 8 branch points. Okay, so I've taken a problem that was sort of, the issue here, the problem here is to take an abstractly given curve of genus 4, just some Riemann surface of genus 4 about which we know nothing at all, and then find some way of writing it in explicit geometric terms. So here there are 2 different models. There's a non-hyperelliptic model where C is just embedded as a plain non-singular quartic, about the simplest construction you can do in algebraic geometry. Or there's a second case where C maps 2 to 1 to P1 with 8 branch points, and then the P1 is embedded by its second Veronese embedding. Right? And I've taken this and I've now written this in terms of these graded rings. So these graded rings, here this is a hypersurface, this one's codimension 2 complete intersection. In general, the canonical ring of a variety of general type, of a curve of general type, surface of general type regular, is a Gorenstein ring, and that's one of the things that I want to exploit later in the course. Okay, so a similar example, similarly easy example, is perhaps the smallest surface of general type that people will ever meet, which is another example. So this is probably 19th century. So I take a surface S, a surface of general type, and I want to assume that PG is 3 and K squared equals 2. Right? So I'm just going to tell you the answer. I'm not going to argue about it too much. Then there's this vector space H0 of Ks. which is three-dimensional. And so I can again choose the basis of it, so x1, x2, x3. And then I can use this to make a map, phi ks, from S to P2. And it turns out that always, now without exception, this is a 2-to-1 cover. A 2-to-1 cover branched in an octic. So this is a curve of degree 8. Which is, let me just say it's reduced and mild singularities. Right, and so if we look at in this case, so I will explain what the canonical class of a surface is and how to use it and what this calculation, what the geometry of this situation is later. At the moment I'm just trying to make a very simple point that there is at least one case here where we can understand everything. So here again I can write down the ring of the surface S and the canonical class. So this is the canonical ring of S. This surface has Q equals 0. I mean, necessarily, or we could assume it. I don't really care. Right, so this is just written by definition, it's the same formula, H naught of NKS. Right, and it turns out in this case that this is K of x1, x2, x3, and then some element Z, and then divided out by an equation F8. And these are graded of weighted degrees 1, 1, and 4. And the equation F8 is Z squared equals G8 of x1, x2, x3. So this is a double cover. If I take the coordinates downstairs, x1, x2, x3, I just get the part of the ring generated by this. Somewhere there's a double cover. So I have to write down an equation Z squared equals something of degree 8. This thing of degree 8 is the branch curve. Right. And this example, this is 19th century. It's probably Max Noether, or it was certainly known to Enriquez and so on. But it has a very peculiar property that if you only consider the linear system Ks and 2Ks and 3Ks, you never see the surface. You never see Z. Right? And so if you want to see what this surface is, you have to go right up to degree 4 in the canonical ring. So I'm going to be talking about canonical embeddings, about these theorems of Bombieri, and this is immediately a very striking counterexample. So in this case, we took curves, and the curves either the canonical class K or twice the canonical class is very ample. Here you have to go up to 4K before you get something which is birational. So in this case 3K is not birational. Right, you need 4K to see the Z. Right. So as I said, there are no technicalities here. I'm not explaining it properly. I'm not trying to say everything here in detail. But in this is a case in which you see the thing which we're trying to do. We're trying to construct the surface S, and in fact we succeed very nicely. Every single surface here, without exception, is given by this construction. But this construction has this funny property that you've got to go up to 4K before you see the whole surface birationally. Okay, so I just mention here two harder examples. So one is I take C, a hyperelliptic curve of genus G, and P in C a Weierstrass point. A Weierstrass point means that 2p is a G12. Right? This is actually a very nice calculation, and I'm going to do it later as an illustration of graded ring ideas. But then if I look at the ring corresponding to C and the point P, then this is, I need generators X and Y and Z, and divided out by a single equation, F. And this one's got degree 1, this one's got degree 2, this one's got degree 2g plus 1, and this one's got degree 4g plus 2. Right? And so this is what happens if I take, here is P1, here are 2g plus 2 points on it. I'm going to take the square root of P1 plus P 2g plus 2. But I'm also going to separate out one of these points as P0. Or, maybe you call this one point P infinity. So I'm really looking at, so z squared equals f 2g plus 1 of y. And then I'm saying, and I want this point here to be a point on the curve here, P. And so the point doesn't move at all. The point is just, this x here vanishes at P. And then x squared belongs to this linear system x and y. So the equation here I've written is an affine equation. And the weighted homogeneous equation is z squared equals f 4g plus 2 of y and x. Right, or you can think of this as 2g, maybe f 4g plus 2, where this is just, this one here is just obtained by putting x equals 1. Okay? So that's an example. The only point about this is that, this is a classical situation. The picture is completely intuitive and so on, but a graded ring picture is sort of rather strange. So I'm going to be doing constructions like this later in the course. And then another example. So this is a curve example, and then a surface example. So this is, if I'm going to look at a surface with PG equals 2 and K squared equals 1. And it turns out that the canonical ring of X, I'm going to call it MS, and KS is K of X1, X2, Y, Z, where these are of degree 1, 1, 2, 5, divided by F10. So I'm going to explain this later. This is just for illustrative purposes. So in this case, S is eventually embedded into weighted projective space 1, 1, 2, 5, degree 10. So this is the pluricanonical embedding. Right. So the point is really, if I just look at this space here, if I stop without the generator in degree 5, this is isomorphic to the ordinary quadratic cone in P3. Right, and then if I put in this F, if I put in the element Z with the equation Z squared equals F10, Z squared equals G10 of X1, X2, Y, then it's, there's a double cover here, and the double cover is branched in a quintic. So it's, it's basically a bit similar to this hyperelliptic case, but slightly weirder. And there is a branch point here which from this point of view, is this surface, this quadratic cone, is an orbifold here, and the double covering is the orbifold covering, is a non-singular orbifold covering of this point. And the branch curve, if you restrict to any one of these lines, I get a curve of genus 2 with a branch locus which is 5 points plus one orbifold point. Right? And so the point about this is that in this case also 4k is not birational. Okay, so you know, the thing that I'm doing here, these are in some sense just interesting examples that will be interesting later in the course. So I'm not doing these at all formally or properly. Right. And so you know, the theorem of Bombieri and others that I'm going to be talking about later in the course is that for every surface of general type, 5k is an isomorphism onto the canonical model. So in particular, it's birational. And then these are the two guys I gave here are the counterexamples. So this example was pretty well understood by Enriquez, quite possibly a lot earlier, I don't know. But it was worked on again by Kodaira and Horikawa and me and other people since then. So, you know, in my career, I started off working on Gödel surfaces and then went on to do threefolds, and now thinking about higher dimensions. What happens in 3 dimensions or in 4 dimensions is still very, very much open research problems. Anyway, let me just sort of start talking about intersection numbers on surfaces. So this is just an illustration of the kind of thing that we want to do later. So intersection number. On surfaces. So S is a non-singular projective surface, and then I've got maybe a divisor. Divisor D is something like some ni di. Maybe I write little di like that, where the di are integers and the di are prime divisors, which means irreducible curve. So when we did Riemann-Roch on curves, then a divisor is a bunch of points, and the reason you want the points is because you want to allow meromorphic functions to have some poles. And so the place where a rational function or a meromorphic function has a pole is a codimension 1 subvariety. That's almost, on a non-singular variety, this is almost the definition of poles of a meromorphic function. Right, so there's a theorem, there exists a pairing. So let me write div of S for all divisors. So this is an abelian group, and there's also pic of S, which is all divisors up to linear equivalence. Right. I'll explain these later, but we don't need them just at the moment. There exists a pairing div S cross div S into Z, written d1, d2 maps to d1, d2. Sometimes it's convenient to put a dot there, sometimes d1 dot d2. And some authors also write d1 comma brackets d2 with I don't like that, but right. So this is a quadratic. I'm thinking of this as being a quadratic form. Okay, and the properties it has: one, it's bilinear form in d1, d2. Right, so it's a function of two variables, and it's linear in either variable. So I don't need to spell out what that means. It means things like, d1 plus d1 primed times d2 equals what you see. Okay, and then 2, it only depends on, let's say, d1 up to, so I'm going to write linear equivalence. Right, so this means that, now let me spell this out. If d1 is linearly equivalent to d2, if d1 is linearly equivalent to d1 primed, then d1 d2 equals d1 primed d2. Okay, so linear equivalence, this means that there exists a function f in K of S, rational function, with a divisor of S. Divisor of f equals d1 minus d1 prime. Right, and so this means that I can find a function which has got zeros d1 and poles d1 primed. So this definition is sort of basically the same as the definition on curves, although what it means is slightly different. Okay, and so I've written these sort of primary requirements. I mean, this is sort of basically assumed in the notation. The first one is assumed in the notation. The second one is, okay. But for example, the function 0, if I just put d1, d2 equals 0, would obviously satisfy these two. So I want to add some non-trivial things. So 3, I want that d1, if d1 and d2 are effective, so d effective means that all the di greater than or equal to 0. Right, if d1 and effective and no common components, then d1, d2 is the sum over all the points p in d1, d2, in d1 insect d2, in the intersection of a local intersection number, d1, d2, local at p. Right. So what's happening here is I'm saying, right, here's my d1 and here's my d2. Right. So if this one's d1 and this one's d2, and they're both meeting at some point here, then I want that d1, d2 at p is something that measures the multiplicity of intersection there. And what we write is we write the local ring OS at P divided out by the equation of D1 and the equation of D2, where so this is OSP divided out by the ideal of D1 times plus the ideal of D2. Okay, so if I'm just doing the local picture in the xy plane, in the affine plane, then I've got I might have, for example, have D1 is given by x equals 0, and D2 is given by y squared equals x cubed. Right, so I might have some right? And then you calculate d1, d2. So this is the local ring OS at the point P, and then it's divided out by x equals 0 and y squared equals 0. Right, so in this case, the thing I've just calculated is this curve here intersect with this curve is 2 points. Right, so you know there are occasions when this is intuitive. Right, at the moment, for example, if I took this curve and I just pushed it a little bit that way, I would get 2 genuine points of intersection. So you can see this corresponds to some kind of dynamic, some kind of thing that you could understand just by moving the curve a little bit and getting the numbers, right? But this definition here, so you know, d1 is given locally by f1 equals 0. Right, I'm assuming that the two guys are effective divisors, which means they're given locally by a regular function. The ideal is generated locally by a regular function. And I'm also assuming that they have no common components in common, which means that the intersection f1 intersect f2 near this point is just this one point. And so, for example, this ideal here contains some power of the maximal ideal of the point by the North-Stern-Satz. And so, therefore, this is finite dimensional. I'm sorry.
Right. Obviously, you mean the multiplicity intersection in 0. Yeah.
Yes.
You want to put in 0.
Yes. Yeah, P equals 0.
Yeah, in the 1 equals 0.
Yeah. Yeah, thank you. Okay, so look, this is so this is telling you the sensible thing. There's a sort of little technicality here, and the technicality is it could happen that the intersection of these curves is really quite complicated. It could happen that one is a little cusp like that, and another is a little cusp like that, and then God alone knows how to visualize this intersection number, right? But calculating this intersection number is usually just a matter of a little bit of local algebra. Right? So this is sometimes a little bit complicated, but it's obvious where the complication comes from. So the second property is not quite so obvious and leads to this strange thing that we're going to write down: curve squared is negative. So this is something which is not intuitive and which it takes some getting used to. Property 4, if C is an irreducible curve. Well, let's say non-singular for the moment. Then C squared is the degree of the normal bundle to S to C. So here's my curve C, lying inside a surface. So there's a normal bundle, which is sort of part of the tangent bundle. Part of the tangent bundle of the surface, which is normal means perpendicular. So this is the part of the tangent bundle of the surface which is orthogonal to C. And this is a certain line bundle on the curve C. So this is the normal line bundle. Right, or it's the dual of IC modulo IC squared. Right, etc. Different interpretations. Or it's the line bundle OC of C. Okay. And so, in particular, for example, if so, we're going to see later that I can have. So note that C squared negative appears possible. Right. And so this is something where you really have to sort of do some examples and think about it before you really become convinced. Okay. So what I've said here is taken from Park City. My Park City Notes, Chapter A. And this goes on to give lots of examples and lots of calculations. So, so I advise you, if you haven't seen this before, that you need to at least read your way quickly through this chapter A. The statement I've just given here, this theorem 1, 2, 3, 4, is there, right? And so this chapter has about 10, 15, basically rather easy examples at the end. So if you haven't seen this material, if you haven't seen in section numbers on algebraic surfaces, please work on this. Maybe I don't know how students here feel. If they want, you know, the one way of working is for students to organise a joint seminar or a kind of examples class. I don't intend to give assessed work. I'm not giving out exercise sheets and so on. However, there are lots of exercises in here, and you know you can't learn the language without doing some of the exercises. Okay, so I'll give later, examples later. You have to sort of work about this to say exactly what you mean by a point. So this is if you say scheme theoretic point, this will be true. If you try to do arithmetic surfaces, then you're going to run into Arakelov arithmetic. But so I'm thinking here that my S is over a field K, which is the complex numbers. Right? So you can also take over any field, or any field. If the field is not algebraically closed, then this point here, you have to think of this point as an algebraic extension, as you know, as a scheme theoretic point. But this property will be true. So that I'm going to give. I'm not going to, as I said, I'm not going to give a proper proof of this theorem, and I'm describing it. I'm saying this is something that you need to know, right? However, I am going to give some kind of background to it and some kind of simpler way of thinking about it. And you know, in a sense, that does answer your question. So you know, if you have a variety defined over an algebraic over a field which is not closed, for example, it's a subvariety of some projective space, then what it means by the degree of the variety is perfectly well defined. And these intersection numbers are really of that nature. Okay? So I've been trying to give this in some kind of you know, if you think of this 1, 2, 3, 4 as a set of axioms, then you know maybe you know everything there is to know, everything you need to know about intersection numbers. So instead of axioms, another rhetorical device is to give a slogan. So slogan, chi of OX of D. So for this purpose, I'm going to just write this chi of D. So this is alternating sum minus 1 to the I of hi of, sorry, this is, I'm still on a surface. Okay, S is the same as X. All right, so this is, the sum here is going from I equals 0 to 2. It is quadratic inhomogeneous function of D. Right, so you know, when you know Riemann-Roch, then you actually know exactly what function it is. But I don't want to worry about the exact statement here. I just want to say this is a quadratic function, and d1, d2 is the corresponding, is the bilinear symmetric form, symmetric bilinear form associated to the quadratic part. Okay, so this is useful. This is really useful because it explains to you how you're going to be able to define intersection numbers in all dimensions and for quite singular varieties. Right? So here we don't need, here I'm just saying something which is, absolutely primary, absolutely elementary piece of mathematics here. Later on I'm going to explain you don't actually need cohomology to say this. This is just something to do with spaces of polynomials. Okay, so so if you know Riemann-Roch, if you accept Riemann-Roch for surfaces, right, then chi of OS of D is, as everybody knows, 1/2 of D into D minus K plus chi of OS. Right? So if you calculate chi of D1 plus D2 minus chi of D1 minus chi of D2 plus chi, you will find that this is equal to D1 D2. Okay, so so this chi here, I say it's a quadratic function of D. We don't even have to be very precise about what it means to say this is a quadratic function of D. This is the S is a surface, chi OS of D is a quadratic, is an inhomogeneous quadratic form. So somewhere in here there's 1/2 of D squared. Right? And if I take, that's a quadratic form. It's a quadratic form defined on a divisor of S or divisor S modulo a linear equivalence. Right? And then what we're doing here is polarizing a quadratic form. So if I do this operation, then the inhomogeneous terms, the terms of degree less than 2 just go away. I'm just subtracting off, for example, the chi of OS here is chi of OS in there, -1, -1, +1. So it appears 0 times. And the only thing that's left is this cross term, is this the associated symmetric bilinear form to a quadratic form. Right? And so, there's an even simpler way of saying this, which I'm going to come to in the second part of the lecture. Okay, so I'll stop now. Students want to talk about how to get hold of this book. So we have this is you're looking after this, or okay? So either Youngnam or Youngju is looking after this. If people want to ask me questions about the direction of the course or about the timetable, we still have some things to decide. 10 minutes?